Welcome back to CMPT 459 Data Mining. This is the last part of the section on pattern mining. In the previous parts, we always talk about mining patterns from transactions. While transactions are a very important type of data, indeed, in practice, there are many other scenarios where pattern mining can find great usage. In this part, we will extend pattern mining from transactions to sequences. That is, we'll consider the orders among transactions and find patterns along those orders. As we note, in transaction pattern mining, we look at item sets where an item is a product a customer purchased. And an item set is a combination of items. And here we do not consider any order, no matter it's a temporal order or some spatial order. And in many applications, temporal orders are very important. For example, we may have time series databases and sequence databases. And we may want to find patterns not only about the combination of items, but also about the order. There are many natural applications of sequential pattern mining. For example, we may look at customer purchase history and look at customer shopping sequential patterns. They may say, well, a customer may first buy a computer and then the iPad and then camera and so on within 3 months. And knowing such a pattern can help us to design promotions and campaigns to help customers get better services. And another important application indeed is medical treatments. We may look at the time order of applying different treatments and their outcomes. And natural disasters may also follow some sequential patterns. By looking at such sequential patterns, we may be able to predict natural disasters early. Science and engineering process are another important example of sequential patterns. And many people look at stocks and markets. They want to find sequential patterns in stocks and markets so that they can understand the consequence of some events. They try to find some early features, early signals that they can use to make their investment more successful. There are also telephone calling patterns, the network, performance patterns, weblog click-through streams, DNA sequences, and gene structures. The list of applications of sequential patterns can go on and on. Therefore, sequential pattern is one of the very major data mining tasks that people like to use. What is sequential pattern? Let's consider a sequence database like this. Here, a sequence is a list of transactions where an element may contain a set of items, and all the items within an element are unordered. We can just list them in some alphabetical order for the convenience. However, different elements in this sequence are ordered. They follow some ordered, for example, in the sequence of the spatial arrangement, or in the temporal order we observe the data. we can define the concept of subsequence. For example, if we have a sequence, say A, B, C, D, C, here, if an element has only one item, we omit the bracket here. So then, what we do is that if we have two sequences, like this one and this one, we can see this A match this A. This BC match this BC. And this D match this D. And this C match this C. Therefore, we say this sequence A, B, C, D, C is a subsequence of A, ABC, AC, D, CF. Similar to mining transaction database, we take a support threshold as the parameter. Suppose the support threshold is 2, and because this sequence A, B, C happens twice in this transaction database. Indeed, if we look at it, we have A, B here, C here. So this sequence, we have that. And also have AB here, C here. So this sequence has that. Okay. So therefore, this ABC is a sequential pattern in this sequence database. Here, there's one thing interesting. Indeed, when we try to match this ABC with the first sequence here, you may notice one thing interesting is that AB is matching here, but for the C here, it can be matched at two places. One place is here, and one place here is here. So you may ask, which one should be used to match this C? Indeed, because we only concerned about whether this sequence is a subsequence of one sequence in the database, we do not mind whether this C match which C. Therefore, either ways of matching works well. And you can see later in the algorithm, we have some way to systematically compute a match between a sequence, a subsequence, and a sequence. There are a series of challenges in sequential pattern mining. First, there are a huge number of possible sequential patterns hidden in a large database. As you can see, like a sequence database, there are many possible combinations. The way to combine the patterns is not only limited to one element. Indeed, it also different elements may combine together to form a pattern. Therefore, the number of sequential patterns can be huge. And moreover, in order to find sequential patterns efficiently in a large database, a mining algorithm has to find a complete set of patterns, satisfying the minimum support threshold. Here, the keyword is complete set, meaning we are not only interested in one or two patterns, indeed, we want all patterns. And also, we want the algorithm to be highly scalable, efficient, and hopefully involves only a small number of database scans, because a database can be large, and then if the mining algorithm needs too many scans, it may not be practical to use. And also, we want to incorporate various kinds of user-specific constraints so that the search can be more focused. How can we mine sequential patterns? One starting point is that we can try to identify some properties, such as the a priori property in transaction databases. That's the anti-monotonicity. Fortunately, the a priori property is also available for sequential patterns. That is, if a sequence S is infrequent, and no matter how you add more elements into S, the expanded supersequence can never be frequent. Let's take one concrete example. Subsequence HB is infrequent. We only have one sequence here contains this HB, H and B. And no matter how you add the item, you add the one element here, say you add A between H and B, then such a sequence can only appear in at most one sequence in the database. It cannot be more than one. And similarly, you can add one item within one element. Again, adding such element, making the sequence even longer, cannot help to increase the frequency. Therefore, any supersequence of HB cannot be frequent. Using this anti-monotonicity, we can immediately develop an algorithm similar to the a priori algorithm for mining sequential patterns. This is the GSP algorithm, called Generalized Sequential Pattern Mining Algorithm. The algorithm works in the following steps. First, the algorithm scans the database once to identify frequent items. Every frequent item in the database is a frequent length 1 sequential pattern. Then, for each level, meaning for the sequences of length k, the algorithm does the following. It scans the database to collect the support count for every candidate sequence, and then it generates candidate length k plus 1 sequences from the length k frequent sequences using the a priori algorithm. We repeat these until no frequent sequence or no candidates can be found. The major strength in the GSP algorithm is that it uses the anti-monotonicity to prune candidates. Let's look at one concrete example. This is our sequence database you saw before. Let's set the minimal support to be 2. In the first scan, we set every single item as a candidate. Then, by scanning the database once, we can count how many times each item appears in the database. For example, how many times A appears in the database, it appears in sequence 10, sequence 30, and sequence 50. Therefore, its support count is 3, and so on. After the scan, for all those items whose support failing the support threshold are infrequent. And according to the anti-monotonicity, we know that any sequences containing such an infrequent item cannot be frequent. Therefore, we can safely prune such items. And the remaining items are the length 1 sequential patterns. Then we can turn on to generate length 2 candidates using the length 1 sequential patterns. This is a little bit trickier than the candidate generation in a priori on transaction database. because we have two ways to make a longer sequences. First, we can do exactly what we do in a priori algorithm on transactional databases. That is, we extend the current element into a transaction containing two items. So we have A and B combined together into AB in one element, A and C combined together into AC in the same element. And you can see here, we only need the upright triangle to record all the new candidates. Because we have 6 candidates here, 6 length 1 sequential patterns here, and then we have in total 6 times 5 divided by 2 is 15 new candidates. In addition to making longer transactions, another way is that we can make longer sequences that have 2 elements in each sequence. So in this case, we have a full matrix here because we can combine A and A into a sequence AA that contains 2 elements. Each element has 1 item A. And similarly, for AB, we have 2 ways to produce longer sequences. One is to have this A, B, and another is this B, A. And in this way, because we have 6 elements here, 6 frequent patterns, length 1 frequent patterns here. So in total, we have 6 times 6 is 36 length 2 candidates generated in this way. In total, combining these two, we have 36 plus 15 is 51 sequential patterns. Length 2 candidates. You can see a priori still helps us to prune a lot of candidates because if we do not use a priori, we will have 8 times A plus 8 times 7 divided by 2, that's 92 candidates. Why 8? Because in total we have 8 different possible items in the sequence database. Now, we can scan the database again to find length 2 sequential patterns. In this second scan, we just collect the support count for each length 2 candidate. And in this scan, you can verify that there are 19 length 2 candidates passing the minimal support threshold. Those are the length 2 sequential patterns. Next, we can generate length 3 candidates. In order to generate the length 3 candidates from the length 2 sequential patterns, we first do the self-join of the length 2 sequential patterns. What I mean here by self-join is the follows. Using sequential patterns AB, AA, and BA, we can generate a sequential pattern candidate of length 3, which is ABA, because you know the ABA, every length 2 subsequence AB, BA, and AA are frequent. Similarly, we can use BD together in an element, BB, and DB, which are length 2 sequential patterns, to generate one length 3 candidate, which is BD together and B. In this way, we can generate 46 candidates in total. Then we scan the sequence database again to verify the support counts of those candidates. And we can find that 19 out of the 46 candidates pass the support threshold and becomes length 3 sequential patterns. The mining can continue iteratively until we either cannot generate longer candidates or all the candidates are infrequent. Essentially, you can see that at the very beginning, we have the length 1 candidates A, B, C, D, E, F, G, H. And then we scan the sequence database once to verify their support. And then we prune those infrequent candidates. And using the frequent patterns, sequential patterns, we generate the length 2 candidates at this level. And we further scan the database again to collect the support information for every candidate. And then we prune all those infrequent candidates. And the remaining one are length 2 sequential patterns. We join those length 2 sequential patterns to produce the length 3 candidates and scan the database again and prune those infrequent candidates. Those surviving ones are length 3 sequential patterns. We continue to generate length 4 candidates and scan the database again to collect the support count and remove those infrequent candidates, and the remaining ones are frequent length 4 sequential patterns. This process can be iterated again and again until we get either no candidates are frequent or we cannot get the longer candidates. You can see here, using the a priori and the monotonicity, we can avoid generating some candidates that are not in the database at all. For example, for this G and H, using the candidates, we do not need to generate any pattern having this G and H. At the same time, the database we may generate some candidates. For example, using this A and B, we generate A, B in one element. Using this E and F, we may generate one candidate is the EF in one element. And those candidates do not appear in the database at all. So those are sort of like a redundancy or ineffective candidates in the a priori algorithm. This is the pseudocode of the GSP algorithm. In the first step of the GSP algorithm, we take a sequences in form of X is an item, as a length 1 candidate. And then we scan the sequence database once. We find F1, which is the set of length 1 sequential patterns. And then we start to do the iteration. Let this K equals 1. Then, if Fk is not empty, and because K equals 1, so that at the very beginning, we look at F1, which is the set of length 1 sequential patterns. We form Ck plus 1 using the self-join of Fk. Ck plus 1 is the set of length K plus 1 candidates from this Fk. And if this candidate set is not empty, we scan the database once to collect the support count for every candidate in Ck plus 1. We prune all those candidates that failing the support threshold, and the surviving candidates become the Fk plus 1, the set of length K plus 1 sequential patterns. And then we increase the K by 1 and repeat the iteration here. As you can see, in this GSP algorithm, the advantage is that we use the a priori and the monotonicity to speed up the mining process, and we can prune many longer sequences if they have some shorter subsequence that are not frequent. But at the same time, there are still some bottlenecks of the GSP algorithm. First, in the GSP algorithm, we have to produce a huge set of candidates. If we have 1000 frequent length 1 sequential patterns, then we will generate 1000 times 1000 plus 1000 times 999 divided by 2 is almost like a 1.5 million length 2 candidates. Why this 1.5 million? Because this 1000 times 1000 is the candidates in this set, this combination. And the other almost like a half million are from this combination within one element. And also, GSP has to conduct multiple scans of the database in the mining process. And if a database contains some long sequential patterns, then GSP has to conduct many scans and also produce an exponential number of short candidates. Just consider a situation where we have a sequential pattern of length 100. Then we need 10 to the power of 30 candidate sequences at least if those 100 items appears in one element. If they are not in the same element, indeed the combination is even more. To tackle the bottlenecks, one idea is that we can use the prefix to produce sequential patterns. Given a sequence like A, ABC, AC, D, and CF, A is a prefix because we started from this A. A is also a prefix. And AB is also a prefix. Then given a sequence, these A, ABC, AC, D, CF, we can have different prefixes. At the same time, we can, for each prefix, we can remove those items in the prefix, and then the remaining items and elements becomes the suffix. For example, for this A here, we remove this A, so we have this ABC, AC, D, CF as the suffix. And for this A and A, because this A is here, the second A is here, so we remove these two items and we have a placeholder here. And then BC, AC, and D and CF becomes the suffix of this AA. Now, indeed, AB is also a prefix of this sequence because we said the items within element are not ordered. So, but because we can sort all the items in an element, so one thing we can do is that we remove this A and this B match here. So we remove all the segments up to this B, and the remaining becomes the suffix. So we have the placeholder here, meaning this place is here, and C, and then AC, then D and CF. Now, using these prefix, we can do the prefix projections. The algorithm works as follows. In the first step, we find the length 1 sequential patterns like A, B, C, D, E, F. And then in step 2, we divide the search space. The complete set of sequential patterns can be partitioned into 6 subsets because we have 6 frequent length 1 patterns. The first subset is all those patterns having prefix A. The second is all those patterns having prefix B, and so on. The last one is the ones having prefix F. As you can see, if you have one sequential pattern, according to the anti-monotonicity of a priori, it must start from one of those items. Therefore, it must belong to one and only one of these 6 groups. Therefore, this partitioning is complete and there is no redundancy. Now, we can try to find the sequential patterns with prefix A. To find all the sequential patterns with prefix A, we only need to consider the projection with respect to A. How to get the projection with respect to A is easy. For every sequence in the database that contains A, we find the leftmost A. And then, like here, in this sequence, we find the leftmost A. And then we look at the suffix of this position. So we have ABC, AC, D, CF for the first sequence. And then for the second sequence, we find A here. This is the leftmost A. And then we get the placeholder D, C, BC, AE, the sequence here. And then we have the third sequence. We have the leftmost occurrence of A here. So the placeholder should be put here. We get the suffix is placeholder B, DF, C, and B. And the last sequence, the A appears here. The leftmost appearance is here. So we have this space holder F, C, B, C, which is this one. Then we find the last 2 sequential patterns having this prefix A, and it can be found from finding the frequent items in these projected database. So we have this A, AA, AB, AB together, AC, AD, and AF. Then we can further partition the set of sequential patterns having prefix A into 6 subsets. Those having prefix AA, those having prefix B, and so on. The last one is that those having prefix AF. It is easy to see that the search of the sequential patterns using the PrefixSpan algorithm is complete because at each node we divide the search space according to the sequential pattern in the current node. And then once we go to the next node, we further divide the search space according to the sequential patterns having the prefix. So therefore, it is complete. PrefixSpan is much more efficient than the GSP algorithm because in prefix, we do not need to generate any candidate sequential patterns. And then we use the projected databases to keep the search more focused, and also the size of the projected databases keeps shrinking as the patterns become longer and longer. The major cause of the PrefixSpan is the construction of projected database, and these can be improved by further projection if needed. And here, I won't go into the details of the bi-level projections, which is a technical detail of the algorithm. If you are interested or you need to use the algorithm, you can look at the related documents. And there are many implementations of the PrefixSpan. And PrefixSpan is effective because the redundancy due to the anti-monotonicity in a priori can be avoided. For example, in a priori based GSP algorithm, in order to produce sequential pattern ABCD, we need to search 15 sequential patterns of the same support. However, we can avoid these. And then we can also define the closed sequential patterns and sequential generators. And we can also define different constraints on sequential patterns. For example, we can say the gap, if two items in the sequential pattern must be no more than a gap threshold within the original sequence. Or we may have the constraint on the length of the patterns. For example, we are only interested in longer patterns, or we may define the more sophisticated application-oriented constraints. Last, indeed, patterns can be found not only on sequences and transactions. We may also generalize into, for example, partial orders. For example, we may have a sequence of customer behavior, like in what order customers may open their banking accounts, checking account, money market account, RSP account, mortgage account, ISP account, and broker account. And then we may find a pattern which is partial order, so that these partial order indeed summarize many sequential patterns. For example, you can verify that these 4 sequential patterns in this database of support to each. However, these sequential patterns can be summarized using one partial order here, and the partial order also has support too. So frequent orders can capture more thorough information than sequential patterns, and there are many important applications such as bioinformatics. We can use these partial orders to preserve the order to form clusters of microarray data. And we may use it in web mining and market basket analysis. We can get the more thorough models on customer purchase behaviors. And we may also do the network management and intrusion detection. And we may do the preference-based ranking. And all those are interesting applications. So in summary, in this long section on pattern mining, we introduce frequent pattern mining. We introduce a priori, FP gross, and HMI 3 algorithms. We also discuss the concise representations of frequent patterns, the max patterns, and the close patterns. And we talk about the frequent patterns with different kinds of constraints. And also, we discuss how to find the statistically significant patterns. And at the end, we also show you how to generalize pattern mining from transaction data to sequence data and find sequential patterns. This is a long section. Indeed, even nowadays, sequential pattern mining and frequent pattern mining are frequently used by industry. And both FP gross and PrefixSpan, these 2 algorithms remained the state of the art, and they were implemented in many data mining toolkits, including the latest like a Spark machine learning libraries. You can find many implementations online. And then in the assignment associated with this section, we will also use those algorithms to conduct some meaningful mining tasks. Thank you, and have a nice day. Bye-bye.